This is one of the first ones that we've kind of dictated rather than applied a vote for. So I'm glad that people appreciate the choice that was made. Um, I just got the warning that my connection is unstable. Can everyone still hear me?
Yeah, so far you're good.
Okay.
You're cutting in and out for me, but you're okay now.
Okay.
You cut out a bit at the end for me too. Yeah, you're still cutting out a little.
I think video is also a little choppy.
Let me swap Wi-Fi's and then I'll try again.
It's like 90% good. I feel like you can just start. It's good enough.
Yeah, it might be a Zoom
Yeah.
thing because like I haven't heard any choppiness, Ryan, so it may be selective.
Yeah, it's
Okay.
not too bad for me.
Okay. I'll
If we
just
turn off our video and mute our mics, we can help him.
So looking back on last week we were looking at the data representation. So you get some real world data you need to format into a tensor so that you can utilize it in some way. And then in this week, what we're learning about is the mechanisms of learning. So they start with a basic example showing Kepler learning from some data. He had some, they didn't really explain in too much detail, but some sort of trajectories. And then eventually he figured out that they were ellipses or ellipses, and he iterated over time to finally figure out that that was the true model and to understand the different relationships. And so what we're looking for in the future now with our more modern technology is to have more generalized models, because it took him years to iterate and find the correct scenario. And what we're looking for here is something that can find that model on a more generalized problem with much less work. So that was kind of the gist of the first section. And then they started posing it as parameter estimation. And so the whole goal here is we're trying to build a mapping from some inputs to some outputs. So you get some new information and you're trying to make some prediction, and you want it to be as close to the real labels as possible. And so we call these parameters weights, typically when we're talking about neural networks. And in PyTorch, that's pretty much always going to be the case. And so the way that whole process works is we've got, I see some chats. I don't know if I should pause for a second. Oh, never mind. So the way this works is the weights or the parameters are applied to the input data, and then it makes some sort of prediction. And then we measure how close that prediction is to the reality of what the data tells us. And then we try to make a correction in order to go in the direction of minimizing how incorrect we are, basically. And so they laid out this example of calibrating a thermometer. So we know the real temperature in some way. We've got some ground truth label. And then we have this thermometer that is unlabeled, and we're trying to figure out what label goes with what actual value. And so they plotted the data and they showed the relationship here is completely linear. And so let's just try applying a simple linear model just to y equals mx plus b. And we'll see if we can find the slope and the intercept of these two values that makes them map to the same prediction, basically. And so to start off, they can look at it in various different ways. They wanted to look at the loss function first, so basically the metric of how close we are to the correct prediction. So the important thing to note with this is that the loss is positive, and we're trying to make it as close to zero as possible. And in order to make that assumption true, you can either take the absolute value of the difference of your predictions, or you can take the square of it. So to put that in more concrete terms, what is it cutting out?
It seems to be intermittent, but there was like a whole, I think, 2 sentences that were missed, and then it seems to come back up.
I
Okay.
don't think it's just you. When I hear Tommy talking, it's cutting out for me too.
Yeah, I don't know what's going on. I'm hearing you cut in and out too.
Should I try with video off?
Yeah.
Maybe it'll lower the bandwidth.
So what should I rewind to the beginning of loss functions? Is that where it was cutting out?
I heard you fine.
Yeah, why don't you just go back to loss function, and we'll just keep going best we can. But definitely if on your audio you miss something and it doesn't make sense, then either chat or just unmute and ask and say something. Ask
Yeah.
Ryan to repeat. Okay.
Yeah. Okay. That works for me. So looking at loss functions, the loss functions are just basically the difference between your predictions and the actual. And so we can look at mean absolute error and mean squared error. Mean absolute error is basically saying what is, so let's say your prediction is 3 above what it's supposed to be, then the mean absolute error would be 3. And if it's 3 below, then it's also going to be 3 because the distance from there is 3. So you're just basically measuring the distance from the correct point based on your prediction. And then the alternate approach is the mean squared error, which is basically saying let's measure the distance, or let's look at the difference between the two and then square them. And that's just another way of looking at that. And they mention in the book, you might have to consider those for different reasons. Mean squared error more heavily penalizes large errors because you're ending up to square your values. And so that's the gist of the loss functions, or the cost functions, sometimes they're called. And then they also mentioned some of the broadcasting rules. And they had a whole section on this. But just to basically summarize, if you have some sort of tensor and you're trying to multiply them or add them or do various different operations, and they don't necessarily perfectly align, if they are the same size in all but one axis, it will just expand it on that certain axis. Or if you're just trying to multiply a scalar or something like that, it will just broadcast that to all of the different values. So you don't have to worry about having precisely the right shape every time. And it's just kind of a convenience, but sometimes it can also cause some confusion. Any questions on that stuff so far?
Hey, Ryan, you cut out for me a lot when you were talking about the broadcasting. I was wondering, like in NumPy, you can do broadcasting, but is NumPy broadcasting more limited? Because I don't remember being able to just like implicitly do extra dimensions and all that kind of stuff.
There's a certain set of rules. I don't know them all completely in detail, but I'd have to look at them. I don't think that it. I think that it can broadcast if you're just missing a single dimension. So if you had something that was 300 by 300 by 1, you could probably add it to something that was 300 by 300. I think it depends on the operation too, though. Does that answer your question?
You cut out really badly for me, so I unfortunately didn't get most of it. But yeah, I mean, the main thing for me was
I've heard the considerations for mean square error versus the other MAE one. But I mean, besides that though, do people really? I feel like there should be a lot put into choosing a loss function, so I'm just kind of curious on what considerations others use for that.
Since
Well,
they're,
go ahead, Hobbs.
I was just gonna say, since they're proportional, it's really subtle. Any small difference you might see in some situations, and the only situation I've ever seen that's ever been a problem is outliers. It's the only thing that can cause either one of them to be better than the other.
Yeah, so you're going to run into different loss functions when you actually have different kinds of outputs, right? So if you have multiple outputs instead of a single output, then you have to figure out how do you, right? So then you deal with, things like categorical cross entropy and stuff like that. But the book actually had a sentence, and I thought it was a fairly good, just general overview, in the sense that if you got the same number for your loss, would you rather have like a couple really large errors, but everything else is like perfectly fit? Or would you rather have a bunch of, 20 small errors and no large errors? And I think for most problems, you would rather have 20 smallish errors rather than having 18 perfectly fit and 2 wildly off. So if that's your choice, if that's the trade-off that you would choose, then you would want to penalize the 2 wildly offs by more. And so squared error will do that. And if that's the case, then in fact you'll have a smaller loss for having 20 small errors than 2 giant ones. Does that make sense?
Yeah, I agree. Thank you.
Cool. I swapped Wi-Fi bandwidths or frequencies, so I'm hoping this should be better. Maybe the rest of my family are just on the other one right now. So let me know if I'm still having issues, but I think that was on my end. That's my assumption, actually. So you were talking about choosing loss functions and the broadcasting rules. I don't know if that question necessarily connected, but we'll move on to talking about the gradients. So in the next section of the book, they were talking about the sort of a black box example. So let's say we have a loss function and we're just trying to optimize it, and we have 2 knobs, and all we're trying to do is minimize this number. And so they have this little graphic here that shows someone on a machine, and all they're trying to do is fiddle with these knobs in order to get this dot to the minimum, basically. And so that's kind of what we can think of we're doing here in this first section, at least with the simple approach that they're looking at. And so there's various different ways to try and move in the correct direction towards making better predictions. And one of them that they're showing is this sort of approximation, where what you're doing is you're measuring above the point and below the point, and you're trying to see whether that pushes the loss up or down. And so it's very simple when all we have is 2 knobs and we just have a single weight and a single bias like we do in linear regression. And so you're just basically saying, does moving this weight make the loss go up or down? If I just jiggle it to the left, jiggle it to the right, which direction seems to be better? Then it's fairly simple to do. But it becomes intractable if you're doing that on many, many different knobs and you've got interrelationships. So they were showing that as kind of the first step. They had a code example where they're doing exactly that, where they're saying push some small delta to the left, push some small delta to the right, measure which direction seems to be better, and then take a step in the direction that seems better. But obviously beyond a certain level, that doesn't really work. And so the second option we have is directly solving for the derivative. So what this is doing is some approximation. It's basically saying if we just look at some small delta, we can figure out what the slope of this loss function is with respect to our parameters. But alternately, we could directly solve for the derivatives, so then we have the exact solution rather than just some approximation. So the way I think of the approximation, it's only loosely related, but looking back at the Riemann sum, if you're trying to find the area under a curve like this, you can approximate it by just basically saying, I'm going to take the area under this, and the area under this, and the area under this. And then if you keep reducing the width of these, then you can basically perfectly approximate the area under that curve. And that's kind of similar concept to what they're doing when they're doing the approximation of the gradients. Is if you just take a very small step in both directions, you can kind of get the general approximation of it.
If you just drew a line for the slope between the two corners of those rectangles in your plot, that would be exactly what it's doing.
Mm-hmm.
It's just approximating the slope as a straight line as opposed to a curve.
Mm-hmm. Yeah. And so they're showing that we can directly solve for derivative, but it's kind of a bear depending on how complex your equation actually is. If you're doing convolutions, if you're doing dense layers after that, if you're doing a bunch of other stuff, then it might become too complicated. So in their example, where we only have a single weight and a single bias, you can directly compute that derivative, but it's much more difficult and cumbersome if you have lots of operations that are stacked together. And so they show that process in the code, and we can talk about that in a second. But the other thing they were talking about is overfitting and overtraining. And so in that learning process, once we have the loss function, once we have the gradient, you're going to iterate through this process of trying to minimize the loss. But the problem with that is you don't know when you've sufficiently minimized it. You don't know when is a good time to stop, because we're just taking steps towards the optimal solution. We aren't necessarily able to directly solve for the optimal solution. And even if we could, it's hard to say if the data that we've seen is going to help us make decisions on later unseen data. And so the concept they talk about is holding some data out and then using that holdout data in order to check how well we've actually learned from the data that we're training on. And so that's sort of the concept of overfitting and overtraining. They have some graphics in there to show that you might have a process where you're learning, and then all of a sudden you switch over from learning to actually memorizing the data, and then you start losing the valuable generalizable knowledge that you've captured from training. And in that example, they also showed that when they didn't have their inputs normalized, they had issues with the gradients exploding and having non-convergence. And so they show that you can solve that by normalizing your inputs, but you can also solve that with a different optimizer rather than stochastic gradient descent. You can plug in Atom or some other optimizer like that. So any questions on that before going into the code? So if no questions, I found this online calculator thing that I thought was kind of interesting. So just looking at the example they were pointing out, they were saying that we have this loss function on that little video game thing, and you've got two different knobs to turn, and you're trying to figure out what minimizes the loss function, and we can kind of do a pseudo version of that. I don't necessarily have directly the loss output, but using this calculator, we can just basically say, let's fiddle with these parameters and try to make it line up the best we can with these points. And so this is kind of the analog to that, is we're saying, let's turn these knobs a little bit and see if we can line them up correctly. would be nice if I could find a way to also have the loss function so we could just be directly looking at minimizing the loss. But I think you can generally tell we've well fit these 3 points that I laid out. So just a little visualization I was able to find really quickly. Getting into the code, same as almost always, we're importing NumPy, we're importing Torch, and then they're showing that we have some data. So this is what they were telling us about, where we have some readings and then we have some ground truths, and we're trying to map these to those basically. And so we put it in a Torch tensor, and then we have our simple model, and our model in this case is that basically the slope and then the intercept. And so this is just a simple linear equation. And then we also have the loss function. So this is the squared differences, they're calling it mean squared error. So basically, what is our prediction versus the correct outcome? And then we take the difference of that and then we square it. And then we just take the mean across that because we're probably looking across multiple different points all at once. They initialize the weights to be ones. It's just a single one. And then they initialize the bias to be zeros. It's just a single bias term. And so this is kind of where broadcasting comes in, because we are doing this across, these are single scalar values, but we might apply it to this entire array. So it has to be broadcast across all of the different points, just something to keep in mind. So with our freshly initialized values, we can plug in some inputs and apply our weight and our bias, and then create some predictions. This is what our predictions look like. And then we can calculate the loss. So this is our predictions against the correct values, and we can see that our loss is very high because it's just randomly initialized to ones and zeros. It's not really anything informed. I'm not sure what that region is doing, just showing an example maybe. And then this is showing that approximation that we were talking about. So they're saying, what is the loss when we plug in? Yeah.
Yeah, so that part that you just skipped over, that was kind of an issue for me with regards to the book. So I think the point of that was that they were showing a diagram example in the book. It's the page that's mostly yellow, that really made no sense to me, because this is, 3 by 1, etc., but the diagram is 5 bys. So unless
I think this is where they were explaining NumPy broadcasting.
Yeah, it's a sidebar, which is why it feels kind of.
But it was a sidebar
out there, but it's a mismatch.
page.
Yeah.
Yeah. So actually, Anne's right. So not only did the code not match the book, but then in addition, in addition to that, this diagram in the middle basically has nothing to do with any of the rest of the sidebar or the code in the notebook. So
yeah, it was weird.
Yeah.
It's actually as if the way I looked at it was like that this image was accidentally pasted in the middle of this sidebar, and you'd be better off if you just sort of pretended it wasn't there, Anne. Okay,
and then so I had one related one just at the bottom of Ryan's screen there, maybe just 1 or 2 more rows down. I mean, I understand, you do you do a 3 by 1 and a 1 by 3, and you get a 3 by 3. But I just didn't remember that if you had that last one, that y cross z cross a, that if you did the y z, you end up with a 3 by 3, and then if you apply a 3 and my terms are off, a 3 element matrix to it, then why is the 3 3 in the second and third position, not the first position? Because I played around with the numbers, and I can start off with A being a 2 by 1 by 1 or a 2 by 3 by 3, and I can get a 3 by 3 to work for it. But if the second two numbers are different, or I mean, the YZ being a 3 by 3 is only applied to the back end of the Y.Z.A. Anyway.
So Ryan, I understood Anne's question. I don't know if you followed that.
Yeah.
Thank you.
So basically we're looking at the Y times Z, that ends up being a 3 by 3 because you're doing a 3 by 1 by 1 by 3.
Yes.
And then I think that what they're showing is there's some witchcraft going on with the A, where it's going, okay, well, a 3 by 3 can't be multiplied by a 2, so it's being assigned to the ones that it can't actually be broadcast across. That's my assumption there. I haven't. It's not that
two
common.
Comments.
It
Go
looks
ahead.
something which works like matrix multiplication, but instead of multiplication, they use summation. So it's some kind of operation of them, you know.
Yeah. So the first thing I wanted to clarify here is the little star, the asterisk that you see there. That is regular plain multiplication. This is not matrix multiplication. This is not vector matrix operations. Okay. So when you see that, that's just multiply. And so I think the answer to your question, Anne, is that PyTorch looks at dimensions starting from the far right and works left. So when you have a 2 by 1 by 1, and then it's got 3 dimensions, and then you've got something that's 2 dimensions, it's not going to try on the left to match the 2. It's going to start on the far right. And so it's going to actually say the rightmost of the 3 by 3, they're both 3, but the right hand 3, it's going to line up with the 1. And it says anytime there's a 1, things work. I'll just broadcast. And then the left-hand 3, it sees another 1 and says, okay, anytime there's a 1, it'll match. And so then it'll just broadcast the 3s across those right-hand 2 most dimensions.
All right, I hear your theory. Okay, I'll play with that. Thank you.
Yeah, so if you had a gazillion dimension thing, you know, a 1 by 1 by blah, 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 by 1 by 1, and you tried to do scalar multiplication with a 3 by 3, it's always going to do it on the rightmost 2 dimensions, is what I'm saying. It'll never do the leftmost 2, even if they're 1 by 1, even if they're, you know, eligible, so to speak, for broadcasting. It's always going to start on the right.
Okay.
There was, just to also address this, there was another question in the chat. They're showing a linear toy example. Should we use neural networks even if the data is linear? I think that if you know for absolute certain that the data is linear, then you can go ahead and use a linear regression, or you can use that as a first starting point step. But typically you don't know that right from the start. So you can apply a neural network and it will be able to solve that. And it's a good general approach because it will be able to find it whether the data is linear or not. But if you know with 100% certainty that there's a linear relationship, then you can just directly use linear regression and you don't have to worry about all of the additional overhead of training a neural network. So this is looking at the approximation step again. We've got our predictions. We're generating our predictions given that we slightly change the weight values, and then we see how that differs with the loss. So they have this equation in the book somewhere. Hopefully I can find it. They wrote out the derivatives and everything. And understanding what they're talking about, they're basically saying the they're looking at the change in, let me just look at the code actually. They're looking at the change in the loss with respect to the weights. So they're basically saying we're going to change the weights a tiny little bit in each direction, and then we're going to see how that varies the loss. That's all they're saying here. And then we're dividing it by 2 because we're taking both steps, and then we're also doing some small delta to factor in what size of movement we're actually applying here. And then from there,
sorry, I was going to say, do you have any idea why they're double ending it? So, you know, like they could have just done the current point plus delta, you know, the current point and then the current point plus delta versus, you know, both sides of it, right?
Yeah. I don't think there's any strong reason for that. It's they also chose such a large delta that they end up the combination.
I do remember something. I remember something good about doing it two-sided, but I'm not sure what it was.
Yeah, I mean, it's
you're
symmetric.
Looking to minimize. You're looking. Well, you're looking to convex it. So if you happen to be in your minima, you'll get a 0 on this. But if you were to do it one-sided, you would potentially move one way or the other, right? So because it's assuming convex functions or convex around this point. All right, never mind.
Yeah. So it's symmetric if you go both sides, and then you're in the middle.
So now we have the change of our loss with respect to our weights, and then we can update our weights. But one thing to note is if we did this with multiple variables, so instead of just having a single W, if we had multiple W's, then we would have to do this multiple times potentially, measuring the rate of change with respect to all of the different weights. So then they also show the relationship with the rate of change with respect to the B, and then we can also update the bias. And so that's the approximation approach. We can take small steps with that, but it's not really tractable. But then the alternate approach is we can directly compute or derive the derivatives of these different functions, and then we can just apply those moving forward. So with the derivative with respect to the weights, we end up just returning TU because we know that it's just it's a linear relationship, so it ends up just being the value itself. And then the bias ends up just being 1 because it's just a constant, so it doesn't actually have any true gradient to pass in. And then this is kind of putting it all together. So this is the gradient of all of the different pieces, and then they're stacking it up and they're summing it because we're doing it across multiple data points. And then they form the training loop. So this is basically saying for every pass through the data, we've got our weights and biases that we're unpacking from the parameters that we passed in, and then we're making some predictions with the weights and biases and the input data. So our predictions are this T_P, and then we're measuring how good our predictions are, and then we're computing the gradient, and then we're correcting the parameters in order to push them so the gradient is smaller and the loss is minimized. Any questions on this stuff so far before we start introducing TensorFlow, PyTorch?
Hey, Ryan.
Mm-hmm.
I don't know. I'm stalling just to give people another moment if they want to ask any questions. You know, I think it's possible that many people have already seen gradient descent, so they already get it even before they read the chapter. That's cool. But if you understand the little cartoon they have about the guy jiggling the knobs, if you understand that concept, then if you don't know the calculus, if you don't understand how they did the derivatives with respect to the W input and with respect to the B input, if you don't know the chain rule, like, that's okay. We're happy to explain it if you want. The book clearly expects that you know calculus and you know partial derivatives to understand those particular paragraphs. But if you don't understand those paragraphs, but you understand just the general gist of the guy jiggling the knobs, I mean, that's sufficient. But if anybody has any questions, I recommend ask now, because otherwise the training loops might not really make sense if you're not at least just comfortable with that in each iteration we're jiggling the knobs and figuring out which direction to nudge the values of our parameters.
I think that that's really the important part to understand, because realistically you're not going to be computing the derivatives by hand in the future and doing all of that manually anyway. It is kind of a fundamental thing to understand what's going on there, but I would say that I haven't actually visited that core concept very often, because it's just handled by TensorFlow and PyTorch and whatever other library you're going to use.
Yeah, and I mean, you even get into issues like, technically, you know, ReLU is not differentiable at 0.
Mm.
It's got a discontinuity of sorts. And so you don't need to know technically. I mean, if you're curious, great, but you don't actually really need to know how it handles that problem.
Mm. Yeah.
To just know that, you know, we're doing gradient descent and we're tweaking our parameters, we're nudging them, and hoping that we keep nudging them sort of downhill to get a nice low loss.
Mm-hmm.
This is just like maybe just a step ahead in what they were talking about, but they mentioned stochastic gradient descent. And in that paragraph, they also mentioned that it's using mini batches. So I found that a little bit confusing to kind of tease those two apart, because there's also a mini batch gradient descent, right? So I'm not sure how they mention those in the same context. I don't know if anyone else was confused about that.
So there's not really a ton of difference between the two in terms of implementation. You can, like what we were talking about with broadcasting, the difference between the two is really just the size of the input that you're passing in. So if you have a single input, or if you have a batch of 10 inputs, the torch tensor or the NumPy array will just broadcast that out across the whole thing. So in terms of actual implementation, there's not very much difference, but the core piece is the stochastic means that you're just taking a single point, and the mini batch means that you're just taking a small batch, so a handful of them. But in implementation, almost everyone is going to actually use mini batches. And then people still call it stochastic gradient descent because it falls somewhere on that spectrum. You're not doing the full batch. You're not doing all of the data. So for whatever reason, people still call it the SGD optimizer, even though it's not necessarily locked to an individual point at every single time. It's still doing batches.
Okay, so there's not like a different one for many batches. You would use the same one.
No.
The size of the batches is different.
Yeah, yeah.
Okay.
Sometimes data is shuffled before picking up a batch. In this way, our data becomes kind of random, and then the word stochastic became justified.
Yeah, I seem to recall at one point, you know, there was a definition of gradient descent where you use every example you have and you calculate the gradient across 100% of your examples. And then there's stochastic gradient descent where you use one example at a time and you calculate the gradient after each example and you update your weights. And then mini batch is just sort of in between, right? You could say, I'll take 16 examples I'll run them all through. I'll sum up what's the gradient across those 16, and I'll update my weights. And so as computing power has become, so available now, really people don't think of them differently anymore. I don't think they're just saying after a certain amount of time, you're going to run your examples through, and you're going to look and see what the gradients are. And every so often, you are going to actually update your parameters. You're going to nudge them based on what your gradient is. And then as you see later in the chapter, and then we'll zero out and we'll start accumulating again, what's the gradient over the next chunk of examples. And so that's why when the authors mention the mini batch, they're saying, yeah, technically it's not really any different. It's just a question of how often do you bother to read the gradients and then nudge your parameters.
Cool, that's helpful. Thanks.
Sorry, this sounds like a very naive question. Just to be clear, the mini batches in Stochastic are subsets of the training data, right? Like there's a bunch of different levels of batching here. And it's just when we do the first batching of training and validation, right? Like ignore validation for the sake of, SGD, because inside of SGD, I'm still going to take my training data and I'm going to sample it to come up with my gradient, just to reduce the time of training itself, right? It's not I've broken it into a training batch and now that's SGD because I have a smaller set than my full data set, right? Does that make sense?
Yeah. So I wouldn't say that. I don't think that's the threshold most people would set, is the train validation split. I think that it's actually just the training process of saying you're taking an individual point, or you're taking 16 points, or you're taking all of your training points. I think that's the difference between the stochastic and the mini batch and the batch. I don't think that people would consider it stochastic when they do the train validation split.
Thanks.
Yeah. So I had to look at this for a second, but I think that these two things are doing the same thing. They just have the additional printouts for the stuff that they generated in the book.
Ryan,
yeah.
I think you're right on that. But my question is, just you're defining training loop twice. Why doesn't that cause a problem?
So it just overwrites the previously known one. So this training loop is never used. It's just basically saying now training loop is this, so just erase all of this stuff. It's never used.
Yeah, in the book, they do it sequentially, where you define the training loop, then they'll run it to show you what it looks like, then they'll define the new training loop. So this, like I said, this example isn't making sense. Why would you define it twice and then just overwrite it? But in the book, it does it differently.
Yeah.
But yeah, there's no, in Python at least, there's no naming collision or anything. You just straight up overwrite it. So this just doesn't exist anymore.
Okay, I'm used to rules-based programming where everything you put in there, it fires whenever it's true. So this is linear top-down. Got it.
Mm-hmm. So they show the training process a few different times, and then here's the graph of what it eventually outputs. And then looking at the autograd, so we looked at the two previous steps, the approximation and directly taking the derivatives. And this is allowing PyTorch to just automatically do it in the background. And so this is a lot of the same stuff, importing the data as torch tensors, defining the model, defining the loss function.
I'm sorry, can I ask a meta question here?
Yeah.
Because I realized you're at the top. So I actually figured out how to, get it on Jupyter and run the code. So for the first one, I had to, it didn't work, it was broken because the matplotlib wasn't there. So then I had to figure out how to add that, et cetera, et cetera. So then I got that set up and it finally got it working. And then I got to this one, to AutoGrad, and I went, well, I'm gonna have to do the same thing, but I ran it anyway and it worked. So, so the system import, the pip, the pip command, it loads into Jupyter indefinitely. I guess my question is, once I exit out and come back in and try to do this one by itself, will I actually have to put that system and pip line command on here to load it up too?
So I think,
okay.
The
Everything which you do,
go ahead.
Everything which you load by pip stays forever in your system. But you still need to import it when you start your program.
And wait, so I did.
So it will be installed in your system.
Yeah, so in other words, Anne, when you run pip install, stuff is being copied to your Python or your Anaconda Python directory. And so that hard disk space is permanently used up. And it also means then that module is forever accessible to any of your programs or Jupyter notebooks.
Yes, it's now in your system. Also, it is not advisable to mix up pip and conda, as far as I know. Conda people, for some reason, advise very strongly against it.
Okay.
It's okay. It's okay.
I think I have a Mac, so I think I don't have conda.
Ah, okay. You could use conda if you want.
I use conda. I like it a lot.
The key to using conda and pip, because sometimes you just have to use pip for some packages, the only thing you can do is to stop using conda as soon as you first use pip, and use pip consistently from then on. That way that particular environment is never corrupted by packages that pip can uninstall but conda cannot.
I just want to,
it's a really,
but
that's all right. It's a really complicated thing when you're trying to use both. I have to use both all the time.
No, I agree. I was just going to add to that is that just to let everyone know, they should also be creating new virtual environments. I know that's a whole other topic, but you don't want to be installing this on your base, you know, package.
So conda
or pip.
Exactly.
Yeah, so I did do an Anaconda PyTorch, whatever you call it, package session, whatever that thing's called.
So you created a separate environment for your PyTorch stuff.
Yes, that's it, environment.
That's great.
You need to make sure you activate that before you launch Jupyter Notebook. Otherwise, that environment. Okay, cool.
Yeah, so I think it was Maya that was speaking just a second ago. So I put the 3 lines in chat, my import and pip and sysexit. So I think what you're saying is that's in my Anaconda environment now, and so I'm good. I won't have to do that again. Is that correct?
Yes, it's correct.
Okay, thank you.
Yeah. Well, you'll have to do import. You have to replace that line of the sys executable pip install matplotlib to import matplotlib.
Okay, that was already there. I think that's Ryan showing that matplotlib inline thing. That one's there.
That sys executable is breaking you out of your local environment that you created so carefully and putting you in your system Python environment. So that matplotlib package is installed for your system level Python. And as soon as you activate your other environment, that goes away and you don't have access to matplotlib. So this doesn't look like to be a good idea unless you're in that base, unless you're using that system Python for your Jupyter Notebook launch.
Oh my.
So I would, so just to simplify things, what you did is you installed it at the system level, which is probably in the end fine because you're going to want matplotlib in all of your environments anyways. But what I would recommend in the future is either you put this in your command prompt or you do the ! pip install matplotlib, and that will do the same thing, and it will install it in the environment that you're already working in. And so when I say the environment that you're already working in, it's going to be across all of your notebooks in the future if you're still in that same environment. So you said you created a PyTorch one. If you're in your PyTorch environment, then you open any of these notebooks and you don't have to install it again. It's just going to be there next time.
Okay, so now I'm remembering, that looks familiar. That's what I did first. I still got an error, so then I went back and found somebody else's example where they used the import sys around it. So then that one worked.
I'm thinking then maybe you weren't inside of your Conda environment when you opened up your Jupyter notebook. So just to put a little context to that.
Sorry for the detour, folks.
Well, this is what Hob was talking about, though, with, you know, if you're going to use Conda or pip, you got to choose one or the other. If you start using pip, then you got to do everything in pip. That's why if you created a Conda environment, a PyTorch Conda environment with your stuff, and then you start using pip, I think things get really confusing at that point.
It's actually fine, Tommy, as long as she does what Ryan is about to show her how to do. As long as she activates that environment, you can use pip. You're just going to always use pip. It's perfectly fine.
Well, that's what I mean. Then after that, you start using pip only. But yeah, anyways.
Yeah, you only use it once. You only use Conda once to activate it, and that's it.
Yeah.
Pip is actually obsolete as of latest versions of Python. Can you just use the Python-m-venv to do that here, and then you're on the right Python interpreter and in the virtual environment?
I was not aware of pip being deprecated. Pip is the recommended package installer by PyP and the Cheese Shop.
I'm fairly sure it's like in the last point release of Python, they're recommending you do the Python-m-venv because that picks up the correct Python interpreter for the virtual environment, whereas you might be running pip off of some other Python system environment, and it gets messy. So it's a very recent change.
Yeah, I don't think we need to comply with that change immediately. That's Python-env. There are many different environment managers, and maybe they're trying to get us all to start using a particular one. But
it's effectively pip. It just pulls the Python interpreter out of your virtual environment rather than pulling the system Python interpreter. I think that's the only difference.
Well, so that they're recommending that you use this particular environment manager so that it will pull out that particular environment's Python, as opposed to pulling out the Conda environment or the virtual env environment or the PyEnv environment. There are a lot of different Python environment managers that manage those directories that contain those environments and those packages. And so this may be the new recommended way.
Yeah, it's not a
but they haven't deprecated pip.
Yeah, no, it's not a new way. It's still using pip. It's just accessing pip slightly differently via the virtual environment. Anyhow, tangent.
So going back to your original question, Anne, whether you use the pip command, the conda command, or a different command, if you say pip install conda install, that is installing the package permanently, adding it to your Python. So it should have worked. Now maybe you were in the wrong folder or something, you know, happened, but generally speaking, if you do it right, and you really should have just been able at the top of your notebook just do, you know, bang conda install matplotlib, and it should have just worked. So I don't know what happened, but generally speaking, you install things only once, and then you can use them for a long time. And you know, I have the reverse problem. I forget if and when I installed things and what versions, and so I have to go and look up and see, you know, how old is my matplotlib because I installed it 3 years ago, and I haven't updated anything since then. That sort of stuff. But I hope that gets to sort of the root of your original question.
All of the discussion is deeply appreciated. I'm still not exactly sure what my right answer is.
Yeah.
Okay. Well, actually, let me actually speak to the sort of the opposite of that. As far as I know, maybe there's some advanced trick, Ryan Hobbs, you may know. There is no way to temporarily make a brand new package available to Python without having it installed permanently. There's no way to say, I want matplotlib, but only just for now, and then the next time I open a notebook, it won't be there.
Yeah. Okay. So yeah, so I got rid of those 3 lines and did the bang pip install matplotlib, and I get an error message, or rather I get a message, a ZSH:1: command not found pip. So maybe this is something I need to
you don't have an active Python working environment. And so I can work with it you offline if you'd like. I'd be happy to share screen and figure it out.
Yeah, yeah, we're off the book, so thank you.
Yeah.
Before go ahead.
If anyone runs into issues throughout the week or whatever, you can feel free to put it in the channel, and there's plenty of people who know what they're doing and can point you in the right direction. That's something that can be deeply frustrating, and we can probably get you over the hump faster than just typing in random commands off of Stack Overflow that I end up doing sometimes.
Yep.
And then worrying if I've actually hosed my Python because I typed some weird, bizarre experimental command.
Yeah. Hobbs, I had a question, because you said that there are some packages that Conda doesn't have. I was just curious which ones, or if there was any that you could recall.
It's about half the packages I install for query. Things, I don't know, like Levenstein distance to, it's a lot of packages. And there have been various occasions for maybe a month or 2 or 3 months or so where TensorFlow wouldn't install or Keras wouldn't install. So what I do is there's very few packages that I install with Conda, and I only do those packages that actually only install well with Conda on all environments like Windows. So things that require binary packages. And so those are the only ones I ever use Conda for. And as soon as I installed those, I never install anything else ever again with Conda. I always use pip, just as in that article referenced by someone Tommy Yu, who posted that chat message.
Cool. No, that's great to know. I try to avoid using pip because of this confusion, but I don't obviously have the same issues as you. I just use more of the generic, packages that everyone uses type of stuff. So that's good to know. Thank you.
No worries.
So looking at the PyTorch AutoGrad stuff again, we've got our model we've laid out, we've got the loss function. All we have to do is make sure that we've got some equation that outputs a number and follows a path that is in some way differentiable. And then PyTorch will just figure out the rest for us. So previously, in the other example, we were looking at a setup where we directly computed the derivatives with respect to all the different variables we were interested in. But in this, PyTorch will just do it for us. It doesn't make that massive a difference when we're only looking at one weight and one bias, but it makes a big difference when we've got multiple stacks of neural network and lots of different variables and stuff like that. So looking at the way this works, we've got our parameters, and we're telling it that it requires the gradient. I think that this is the default actually. So this is just them explicitly showing them turning on the gradient requirement. And so we've got our initial weight and our initial bias, I believe is what they're showing here. And then they're just checking our gradients there. And then they're computing the loss function. So we are making predictions given our input and our weights and our bias. And then we are comparing that against the true answers and then computing our loss function. And then PyTorch does all of that magic that we had to previously calculate by hand by just calling backward. And then we can look at the gradients that are applied there, and it's saying that we need to so this is the error on the weights, this is the error on the bias, basically. And then they show training loop. This looks almost exactly the same as the previous one, except for instead of using our own gradient calculation, we just have to do the loss and then apply the backward step. And then we can apply that gradient in the opposite direction on parameters. And then we can print out our loss, and we can see that it converges to roughly the same spot as the previous example where we were doing it by hand. Any questions on that so far?
Hey, Ryan, not so much a question as just a comment that, like, whatever, the left side of my brain understands what the code does, and it makes sense, and I can write that code if I need to, but there was a part of me that at first was just a little confused that, oh, I'm calling backward on the loss, but that's not giving me gradients for the loss tensor, it's giving me gradients for the params tensor.
Mm-hmm.
So I don't know if other people kind of had that same little, just like little mental moment, but when I first saw that, I was just like, at first, that was a little bit confusing.
Mm-hmm.
Because I was sort of expecting to see something that said params dot do something to calculate the gradient.
Mm-hmm.
Right? But it's not coming from params, it's coming from loss.
So what's happening here is it's built its whole graph. So it knows, okay, our model gets this input and it's got these parameters and all of this stuff, and then it goes into loss. And so it's just a series of functions that it's going through. And then when it gets all the way to the end, the loss ends up being that single scalar value. And then you call backward, and it's actually going backward through the whole graph. And that's how it calling this backward step is what actually does that backward pass. And that's when the gradient is actually calculated. So if we blocked out this, if we never called the backward step, I would assume that this gradient is never actually calculated, or it would be just zeros or something like that. That's at least my understanding of it.
To that point, I mean, it accumulates the gradient on all of the tensors which show up in that tree, in that graph. So technically, there is, you know, I was going to say a loss tensor, but I guess it really isn't a loss tensor. And I think this kind of shows up more in the next example, but it's if you had multiple steps there, where there were like, you know, there's multiplication, there's an addition, and there's another multiplication and addition. Each of these are creating partial tensors. As it goes back up through that graph, it's going to create a gradient on all of them. It's just that the only one we're looking at or care about is the gradient on the parameters, because we need to know which way to move it, right?
Yeah. And so the other thing is they're using this trick here, saying with torch.nograd. So they're not calculating the gradient for this piece. And that's kind of important, because they're saying we don't want to accumulate a gradient on this graph when we're making the actual update step, because that's going to cause other issues down the road. Just something
it's worse.
to keep in mind.
It's worse than that, right? Because since in Python you can redefine the variables, like basically what happens after this subtraction operation is the params variable gets replaced with this new value. So, but this value has in it part of that computation graph that says, hey, there's this previous value which was assigned to params a while ago, and so, but it's still there. And then you do this again because you move on to your next epoch, and it's like epoch, and it's like, oh, okay, now we're like 2 graphs deep, but they're all chaining back. So if you're doing it that way, then you're inherently constructing this, you know, 25,000 long graph that is going, and every time you do an operation on that, it's going to get the backwards, it's going to calculate the backwards all the way up that graph, even though it has no meaning to you because you've kind of thrown away those values. So you're adding a lot of memory and CPU utilization.
Mm-hmm. It's interesting. I just tried running it just to see what would happen if I turned off this nograd step, and I just tried to actually do it. And it's interesting that it actually throws an error. So
it's got a safety on there. Yeah,
yeah,
that's good.
So that's
Sorry, I had a real quick question. So with the grad, I guess, values that it's stored, is it kind of like, so if you do continue operations on the grad to do the grad and zeroing it out like they had earlier, is that overwriting the previous ones, or is that creating like an array of different gradients?
It's accumulating them.
Yeah, it's going to sum them, Tommy.
Yeah.
So it sums them up?
Yeah.
Yeah. So if they were all the same sign, like if they were all positive, then that grad would just keep getting bigger and bigger and bigger and bigger forever.
Is there I guess it's interesting to me that it sums it. Is there a reason that would be the default behavior? I mean, I guess another use case.
I thought it had to do, or
I don't know if your
thought it
audio...
had to, go ahead, Ted.
Oh, sorry. Tommy, I don't know if your audio broke up, but what I heard, the question I heard was is the reason why the default behavior is summing. And it's because, like the question before about batches, is if you do one example, then what you do next, I don't know if anybody can predict what it is that you want to happen, but if you're doing a mini batch of 16 examples, what you want to do is to sum up the gradients across those 16 examples. So that's why the default is to just keep summing.
There's, you can take the sum or you can take the mean, and there's actual, that was something that really confused me about PyTorch and TensorFlow at the beginning, was they use them differently. So I would see that my loss on one would be really high and my loss on the other would be much lower, because one was taking the mean and the other was taking the sum. So on one, it would be like your loss is 13 and the other one would be your loss is 0.2. And the thing that was confusing for me is when you're taking the sum, your loss is actually scaling with your batch size, which seemed weird to me, because on the TensorFlow side of things, when you're always taking the mean, you can kind of interpret it saying like the average result is whatever. So if your binary cross entropy is 0.1, that actually means something, and no matter what your batch size is, it's always going to be the same thing. But if you change it to the sum, then all of a sudden you're getting this value that just fluctuates with your batch size, and that didn't make sense to me. But you can do either, is part of my point. You can take the sum or the mean.
What sum do you mean? Can you please point me out? Because at some point the sum is vector sum, meaning that it is entry-wise. You don't sum all values of our partial derivatives. They all act in not together, but they all act on its own direction.
Mm-hmm. So
you still want to normalize that down, right? Otherwise, you will get a huge magnitude there, right?
So I'm talking.
What do you mean normalize? They're not summarized together. Each of the partial derivative acts on its own direction, and that's it.
So
they're not summed together.
So
it is a vector sum, not numeric sum.
You need a loss for each of your inputs in order for it to make sense. I'm talking about the summarization when we get these down here. So when it tells us that the loss is 45, 26, and so on. So when we get the summary out at the end, just to say general performance, that's what I'm talking about. I'm not necessarily talking about it during the calculation.
Oh, yeah, I see.
But I think the other thing that I was commenting on, Ryan, is if you run one example through and you call loss.backwards, you're going to get the gradient for just that one example. But if you ran 16 examples through and you did not call loss.backwards at all in between, and then you called loss.backwards after the 16th one, you would get the sum of the gradients across all 16 of those examples.
I think that it might actually be storing the full history of it rather than actually doing. I'd have to look at that, because I'm not sure how that would work, because it has to keep track of the I'd have to look at that more closely.
Yeah. Yeah, and I actually don't know technically if it's sum or mean, but my point is that it is summing it across. And so if you had, say, I don't know, if you had some giant thing and you ran 1 million examples through and you never called loss dot backwards, like if you were trying to do full batch gradient descent, okay? And so you had, only at the end of your epoch, of 1 million examples did you call, it would work. And my understanding is that PyTorch is not going to explode in memory because it's not going to keep track of the 999,000 intermediate steps. It's just going to accumulate that gradient across until you finally call loss dot backwards, and you'll be fine. There'll be no memory issue because it's not tracked. You know what I'm saying? It's not keeping that history in full.
I understand what you're saying. I'd have to look at it to see if that's actually the case because I'm not entirely sure.
In any case, if all your batches,
Go ahead.
If all your batches of the same size, then losses are comparable for each run. So it is not necessarily to divide them by the number of elements in the batches, number of records in the batches you use.
I had another random question unless someone else has something on this topic. So I'll wait. Okay.
Yeah.
Ryan, I noticed when you ran your entire notebook that did you scroll with the execution or did that do that automatically?
Did I scroll with the execution? I don't know what you mean by that.
So like each cell was being highlighted in the center as it executed the cell. So it scrolled down from top to bottom. Was that you scrolling or was that something that you enabled in Jupyter?
That's just the default behavior, I thought. I haven't done anything special in that regard.
So Tommy, I don't think it was running as it executed. I think Ryan was just doing Shift Enter. So it was scrolling along with his active cell, but the ones that were running were just being updated off screen. I don't think it was actually keeping focus on which cell was actually running.
Yeah.
Oh, okay. I thought that was the case. So I was like, that's really cool. And I want that. Anyways.
Yeah, I want that feature too.
Yeah.
Yeah, no, I'm just hitting Shift Enter, so it's just pushing me down to the next cell, and it just happens to be that all of the ones are executing basically in real time because none of these take very long to run. So that's all that was happening there. Going back to the notes, we talked about this, we talked about this. So sometimes you want to turn the gradient calculation off so you can directly say, don't calculate the gradient for this specific tensor, whether that be weights or something else. But you can also do that wrapper like we saw in the code. So if you have just a extended section, you just say, I don't want gradients calculated for this entire series. You can just do this with torch.nograd, and then it will say, okay, don't calculate a gradient for any of these. So that's also an option. Calling the backward to get the gradient, and then you have to zero it out like we just discussed. And then talking about optimizers. So we can look at optimizers here. Same as the other ones, same data, same everything, same model, same loss, and then just looking at the optimizers. So there's several different options here. There's argument for many of these. I tend to default to Atom at this point, but some people say there are other better ones now. Some of them even outside of this package, but Atom's a good default. SGD is another one that a lot of people use. So we have our parameters for our model, just like before, our weight, our bias, our learning rate, and then we just take our optimizer we define it and we say, these are the parameters I want you to optimize for. Here's the learning rate. And then we do kind of the same thing as the previous one. This is just doing an additional simplification on top of what we were doing before, where we define our loss function, define our model, do a backward pass on some predictions, and then we do a step with the optimizer. And this is just replacing some of this stuff. So it's really basically replacing this step. And so this is just basically stochastic gradient descent. This is just a simple equation, but sometimes it can get more complicated than that. Adam has additional parameters and other things that it's keeping track of. And so in order to keep it simple, you can just basically say, I want Adam, I want SGD, and just plug in the different ones. And then you don't have to hand code the full optimization algorithm every single time. And you can plug in new optimizers when they come out and stuff like that. So nothing too interesting on this front, just kind of the same operation, but just hiding some of the mess of actually calculating it by hand. Any questions on that front?
For me, Brian, the main thing was just knowing that the terminology is step.
Mm-hmm. Yeah.
Yeah, epic or batch or whatever. I mean, that's just the terminology.
I just cut out for a second. I missed a bit of what you said, but I think I got the gist of it.
Sorry, it wasn't a question. I was just saying, for me, it was just getting clear on the terminology. We've used the term batch or mini batch. We've used the term epoch, which is all of your training data. And so then step, typically in my usage, will correspond with a batch, but it's when you're talking specifically about the optimizer. And if you read up about how the optimizers work, then they'll, right, instead of just multiplying the gradient by the learning rate, they're doing more advanced things. And so they'll use the term step. So in a step, it will do X. And then they'll talk about momentum or whatever they'll talk about.
Yeah. So I think the last section of the chapter, they're showing that we can split a train and validation set using this torch.randomperm section. So basically this is saying the number of samples, so the size of our data. And then we are just basically splitting the data into train indices and val indices, and then we're grabbing that directly out of the data for both the inputs and the labels, and then we can map that to a training set and a validation set. And this is just kind of redefining the training loop, so we also have some validation in there as well. I don't typically do it like this. I typically don't do it with Torch. I don't know if there's a strong reason why you ever would. I typically use the scikit-learn stuff that can help you split data in various different ways, either stratified or k-fold or various different methods. So this is interesting to look at, but I don't personally use it that much. And then another side comment is this training loop is probably going to be very, very similar in almost every single project that you do. And what's happened is a lot of people have built frameworks like PyTorch Lightning and Ignite and various other things that simplify this, so you don't have to actually write any code for this. You just directly say, this is the optimizer I want, here's the model, here's various other parameters that you might want, here's the loss that I want you to optimize for. And then it replaces all of this code, and it can also do nice logging stuff and various different metrics. So I would say that most people will probably write this loop once and then always use it, or they'll borrow someone else's. So I wouldn't worry a whole ton about this. I basically just copy and pasted the same old one that I've had for every project and then just made slight tweaks if I ever have to.
You said PyTorch Lightning or what? What was the other one you said was
There's a whole bunch of options. So PyTorch Lightning seems to be the one that's gaining a lot of steam. But there's also the other one I said is Ignite. So this is a good one. And this is Ignite. So they'll define a trainer is what they call it sometimes. And then there's also Catalyst, which is another one. There's a whole bunch of options. You kind of just have to look through and say which one has the features and the implementation that I'm interested in. Most of them have stuff that you're probably not going to care about that much starting off early on. And it's probably better to just start with vanilla PyTorch to start and then branch off if you see that there's something nice that you want there. But that's just my 2 cents. So any other questions or general discussion points? I think that's pretty much all there was in this chapter from the book. If not, maybe breakout rooms.
Yeah. So let me just do a couple quick admin notes. So so Monday's Labor Day. So for some people this will be a little short, and so by pure coincidence, chapter 6 is actually a light chapter. So it's only about, we've been doing 30-page chapters, and it's only about 20 pages. So if you've got some plans or other stuff, the good news is it's a little bit of a lighter week. And then I actually have a poll that I'm going to throw up. I realize some people had to leave. I think that some people might not be here because of the holiday weekend. So I think I'm actually going to put it up again next week. But